So today we're going to pick up where we left off last class, which was just getting done with the idea of odd and even functions. So now we're going to be talking about annuities and the amount of an annuity. The amount of an annuity is just going to be the average of that function. So what this is going to look like is going to be, I shouldn't call it the average, it's not quite the average, but it's the same general idea. 0 to t, that should be the CT, yep, C of t, ER, negative ERT, dt, where t is time. So this is going to be the equation for the amount of an annuity. Really what it just tells you is how much money is this annuity going to collect over time? That's really all we're getting at. So just a quick point, because I think the notation is a little confusing. These are both constants. The book uses capital T, but they're just constants. It represents the time that the annuity ends. Does that make sense what I mean? And since we have so many other T's, I think, like I said, notation is a little confusing here. So having said that, since this is going to be the amount of an annuity, we're probably going to use it, right? And for folks at home, this is slide 42 of week 13. You can find it under exam 4 on Blackboard in the course material tab. And in this example, what we've got is an initial deposit of $200 each year for 15 years. So what we're going to be doing is depositing $200 each year. So CT. $200, my mistake, 2,000 I mean to say. Now, we're paying 15% interest. So that's going to be R is equal to 0.05. And this is going to be over 15 years. So capital T is going to be 15. So to calculate the amount of this annuity, all we're going to do is apply that equation from the previous slide. So we're going to say, all right, cool. The amount of this annuity is, let me use a different color chalk. The amount of this annuity is going to be E 0.00, my mistake, 0.5 times 15 times the integral from 0 to 15 of 2,000 times e to the negative 0.05 t dt. So comparing, exactly what they wrote out, right? So after we do the integration, this is going to come out to be 2,000 times e to the 0.05 15 times e to the negative 0.05 t, my mistake, excuse me, yeah, t over 0.05 from 0 to 15. You got my negative sign. Now I'm not going to pretend to even try to do this calculation because I have no clue what e raised to the 0.05 times 15 is. I have no clue what that is. So I'm going to leave it in this form for right now and just reference what they claim the solution is. So approximately. And the reason why it's going to be an approximate solution is because E is a non-repeat or non-terminating decimal, non-repeating, non-terminal. So you're going to get a huge long decimal on the back end of that. Make sense? So, having said that, there's another question that actually pops up when we start talking about area of integration, or rather when we start talking about area and definite integrations. So we understand that, let me make sure this is turned up too. Cool. All right, now I have volume on there. All right, so like I started saying, a natural question pops up when we start talking about integration. You understand that the integral of a function is going to give us the area under the function between two x values, right? So this makes sense. This is what we've been talking about up to this point. But what about now, if I want to change this a little bit? What if now I want the area of something like this? This is g of x. We want the area here. How are we going to find that?
Find the area for what's under f of x and subtract the area of g of x from it.
Exactly. Exactly. So the first thing we can do is say, all right, let's find the area under f of x, then let's find the area under g of x, and let's subtract the two. So writing this all out, there's no nice, easy way of doing this, so what I'm going to do is say, what I'm going to do is say that A, our area here, because that was weird. It dropped the Wi-Fi here and everything else. Okay, hit record again. We are recording. Cool. Sweet. All right. So I'm going to go back to the slides. Okay. So backing up for a second now. We understand that the integral from a to b of a function will give us the entire area under that function between x is equal to a and x is equal to b. So if we want to find the area between two functions now, we're going to take the area of the largest area and subtract the area underneath the smallest function, right? So we're going to get something that looks like this. Make sense what I mean? We're trying to find this area through here. But notice when we do that, we can rewrite these two integrals now. We can rewrite them as the integral from a to b of f of x minus g of x dx. So the area between two functions is going to be the integral from a to b of the difference of those two functions. Everybody cool with this? So just as a visual example of what's going on here, we're trying to find the area between these two. We start by saying, hey, what's the area of F between A and B? Now what's the area under G between A and B? Take the difference and you get this. So, given that F is greater than G, we can rewrite the formula this way. Make sense? And what we're saying here is that in the event that g of x is the smaller of the two functions, then the area between the two functions will abide according to this integration. That's all we're saying here. If, however, it flips, then we would flip them. Get what I mean? So, looking at this first example, what we've got is the area between x squared plus 2 and x. So x squared plus 2, it's going to look something like this. Except more symmetric, less cattywampus. Okay, so this is x squared plus 2 is equal to y. And now, we've got the other equation, x is equal to y. What we want is the area between 0 and 1 and these two functions. We're trying to find this area here. The first thing we need to observe is that x squared plus 2 is going to be greater than x whenever x is between 0 and 1, right? So this is going to play the role of f of x, and this is going to play the role of g of x. Make sense what I mean? So this integration then is going to come out to be the integration from 0 to 1 of x squared plus 2 minus x dx. So when we do this integration, this is going to come out to be the integral of x squared is going to be x cubed over 3. The integral of 2 is going to be 2x. And the integral of x is going to be x squared over 2. And this is going to be evaluated from 0 to 1. Now the book rearranges it. They say, hey, we can just go ahead and drop all these parentheses and group them together like a normal polynomial and integrate it just like we usually would. But in the end, we're going to get that our antiderivative, once we do this evaluation, is 11 over 6. Our indefinite integral, or my mistake, our definite integral is what I should have said. That is going to come out to be 11 over 6. Make sense? Okay. So, what about in this case now? We're changing it a little bit. Here, in this new example, our integral or our functions change only by a single sign. And let me draw this out. Good, good. I did not tell you all that. All right, so this is the line, x is equal to y. And this is 2 minus x squared is equal to y. We want to find the area bounded by these two functions. So my drawing up here is really poor because what we actually have is a shape that looks a little bit different than what I've got up here. It's a little ambiguous. So let me draw this better. It looks something like this. This is 2 minus x squared is equal to y. And this is x is equal to y. The area we're going to find is through here. How are we going to do this problem? What do y'all think? Okay, so first, let's just set up the integral. we know the integral is going to be the integration of, well, it looks like this is our largest function, right? So it looks like it's going to be something like 2 minus x squared minus x dx. What are our bounds? Excuse me. Well, our bounds here are going to be A here and B here, right? So how are we going to find those 2 points? What are we going to do? We're going to have to set our functions equal to each other and solve. That way we can find out what the interval is going to be. Another way to think of this is to say that if these 2 functions are crossing each other, then their y values have to be equal and their x values have to be equal, right? So by solving where they're equal to each other, we find the bounds. Okay, so what we're saying then is 2 minus x squared is equal to x. This then tells us, subtracting all this from both sides, 0 is equal to x squared plus x plus 2. Looks like we need the quadratic formula, doesn't it? My mistake, I meant to write minus 2. I apologize about that. It almost looks like we're going to need the quadratic formula, except for the fact that this can factor out. When we factor this out, we get x minus 1 times the quantity x plus 2. Okay, so when is this thing going to be 0? When x is equal to 1, right? And this thing's going to be 0 when x is equal to negative 2. So here, we know that x has to be 1. And over here, we know that x has to be equal to 2, or I mean negative 2. So our bounds are going to be from negative 2 to 1. Now from here, we do everything just like we would normally. We integrate everything out the same way we have in the past. We've got our f, we've got our g, subtracting the 2. We've got our bounds, so we're just going to integrate out. Everybody cool with this? Folks at home, does this make sense?
Yes.
Awesome. Okay, here's another problem. This one's not quite as clear, I don't think, as the last one. What we're going to do here. This problem's saying we've got x squared minus 3x minus 4. First question to ask, can we factor this out? The answer is yes, we can. So writing this out, x squared y is equal to x squared minus 3x minus 4 minus 3x is equal to, this is going to come out to be x minus 4 times x plus 1. Feel free to check me. What this tells us then is our graph is going to look something like this. And I'm going to move this over and make room actually. Going to look something like this. And this is, of course, f of x equal to, this is going to be x squared minus 3x minus 4. What the factorization told us is that this thing is only going to be 0 when x is equal to 4, and when x is equal to negative 1. Agreed? Now, we want to find the area bounded by the graph and the x-axis. That's this area right here. Excuse me. Okay, so let's think about what the x-axis represents. If we were to write an equation for a line that lies along the x-axis, what would that equation be? Well, this would be the line y is equal to 0. Agreed? Okay, now in the region of our integration, -1 to 4, that line is greater than our function, right? So the integration then is going to be from -1 to 4 of 0 minus x squared minus 3x minus 4 integrated with respect to x.
So it makes it negative, basically.
Exactly. Exactly. What's going to happen now is that all we're going to end up with is the integral from -1 to 4 of negative x squared minus 3x minus 4 integrated with respect to x. Which we can rewrite because we can distribute this negative sign all the way through. So we're gonna have negative x squared plus 3x minus, my mistake, plus 4 dx. We're gonna integrate that and then apply our bounds. So looking at the next slide and comparing everything, exactly what they're trying to tell us with this graph, right? The shaded area is in fact below the x-axis. And estimating based on the numbers provided along the x-axis, our graph does in fact go through -1 and 4, right? So like something like this. Now, jumping to the next slide and looking at the actual solution to the integration, they factored out the equation. They found out where all of your intercepts are. They said, okay, you've got an x-intercept at 4 and at -1. So your bounds must be from -1 to 4. Rewriting this as f of x minus g of x. F of x is going to be 0 minus g of x. G of x is going to be x squared minus 3x minus 4. We're integrating all of this with respect to x. Rewriting now our integrand. We get negative x squared plus 3x plus 4. Doing the integration, we're going to get negative x cubed divided by 3 plus 3x squared divided by 2 plus 4x. From -1 to 4. So after we do that arithmetic then, we get 125 over 6 square units of area. So really, the hard part here is just the setup, right? It's going to take some time to know how to set each of these up. We're not always going to be given our bounds. And because of that, there's going to be some trial and error with some of these problems. Massaging the algebra until we figure out what the bounds are going to be. 9 times out of 10, what you want to do is set your two functions equal to each other and solve, or you're going to want to set your function equal to 0 and solve. 9 times out of 10, not every time, but 9 times out of 10. So jumping ahead to another problem, this one is a lot more involved. So first, we've got two functions, f of x, which is equal to 3x cubed minus x squared minus 10x. Before we do anything else, notice you can factor out an x. Pulling out that x, we get 3x squared minus x minus 10. No factors are jumping out at me right away. Now, the next function is g of x. and it's equal to negative x squared plus 2x. Right away, we can pull out a factor of x. When we do, we're going to rewrite this to get 2 minus x. All I did was just flip the terms, right, and then factor out that x. Now we're going to use some facts we know about the geometry of polynomials. In the cubic, the leading term is positive. In the square, the leading term is negative. They tell us about the direction these things are going to point, right? We also know they both go through 0, just because they both have that factor of x pulled out. So when x is 0, our function has to be 0, right? So we know it has to go through the origin. Looking first at the orange one, at g of x, or I mean the pink orange, the pink one, we know we have this point, and we know that when x is equal to 2, this thing's going to be 0. So we've got a point over here, and it's going to be looking like this. Yeah. Let me rewrite that because that is ugly. It's going to look something like this. Oh my God, I can't draw. All right, we're going to pretend this is nice. Okay? Squint your eyes, tilt your head sideways. This is abstract art. Okay. Now, in the cubic, because that leading term is positive, over here we're going to be going up, and over here we're going to be going down. I don't know how to factor this out right off the top of my head. All I know is that we're going to go through the x-axis. The general shape is something like this. I think we have another intersection down here, though. Let me look. Yes, we do. I way underestimated this. Okay. So our graph looks like this. Pulling way down, coming back up. And then intersecting somewhere over here. So the area we're looking for is this stuff here. So what do you think we need to do here? What's happening? What do we need to consider? Well, the first thing we need to consider is the fact that through here, f of x greater than or equal to g of x. Right? And through here, f of x is less than or equal to g of x. So we're going to need to break up our function or our integration into two parts. We're going to need a part that considers just this bit, and another one that considers just this bit. So this and this point are going to have to be solved by setting our functions equal to each other, right? And solving for them that way. When we do that, we find we get 2 of 0. So this here is going to be -2. Up here is going to be 0. This is the -2, -8. Is that point right there? 0 and 2 zeros right there. Okay, so this is going to be f of x minus g of x dx. That is that area right there. And then this area down here is going to be from 0 to 2. G is larger, so it's going to be g of x minus f of x dx. Then we're going to have to add these together. I wish this chalkboard was bigger and I didn't have the projector going right now. But what we're doing, first and foremost, we're saying, hey, we can factor out this x in both equations. That's convenient. Now, we've got to set these things equal to each other. So if we can factor out this x, and it's where they're equal at 0, they're going to factor out down the road, and we only have to consider what's inside of these two parentheses. Make sense? So, setting those equal, solving, gives us this point over here, -2, -8. And this point right here, 2, 0. That's how we know the bounds of integration is from -2 to 0. We're going from -2 to 0 here. And in this region, our function f of x is greater than or equal to our function g of x. And in this region, we're going from 0 to 2. G of x is larger than f of x. So our integration is going to be from 0 to 2, the g of x minus f of x. Both of these are going to be integrated with respect to x. When we're done, we're going to add the two areas back together. Make sense? Folks at home, does that make sense?
Yes, it does.
Awesome. So, walking through what they've done up here. They started off by just setting the two functions equal to each other. And then they said, hey, rearranging the terms, we can add x squared to both sides and subtract 2x from both sides. We're going to get 3x cubed minus 12x is equal to 0. Okay? Well, that 3x, now we have an x that we can pull out and a 3 that we can pull out. And what we're gonna have is 3x times the quantity x squared minus 4. That factors out nicely to give 3x times the quantity x minus 2 times the quantity x plus 2. So we know that our intersects are going to be at x is equal to -2, x is equal to 0, and x is equal to 2. So they went about solving this a little bit different than what I would, but it does the same thing. Now, they said, all right, cool. We've got 3 intersection points, and we need to make sure we know how our functions compare to each other on those 3 intercept points, or between them, I should say. So comparing them, f of x is larger. That's what they're saying here. I'm going to say here. And then f of x is smaller, between 0 and 2. So the area is going to be the integration from -1 to 0 of f of x minus g of x, integrated with respect to x, plus the integral from 0 to 2 of g of x minus f of x, integrated with respect to x. From there, we're just going to do the algebra and the calculus, right? We're going to substitute our functions back in, reduce everything nicely, massage the algebra. So integrate, massage the algebra down here, do the arithmetic, and the answer comes out to be 24. So for those of y'all at home, this was problem 55, or page 55 in the notes. So having said that, there's a new concept that we're going to be talking about. This new concept is the idea of consumer surplus and producer surplus. What we've got, I'm going to draw it out here on the board. What we've got is a failure to communicate. I don't know that reference. You're too young to be in my class. What? And what else do I want to include? This is the demand function. This is the supply function. This, I'm just going to write as A. Come over here, this is P naught. So what we're looking at right now is a graph of the supply function and the demand function with the points of equilibrium being marked, right? We're going to say that the area underneath the line, y is equal to P, P naught, the area underneath it is the producer surplus. And the area above it is the consumer surplus. So if we want to find the consumer surplus, what are we going to do? I'm going to call this AC, and I'm going to call this AP down here. What are we going to do to find AC? Well, we're going to take the integration of our demand function, which I'm going to just say is d of x right now, since that's what I'm doing up here. All right, so it's going to be the integration from 0 to a of your demand function minus P naught, or the price of equilibrium, integrated with respect to x. That's going to be equal to AC. Meanwhile, AP, that's going to be P naught minus your supply function integrated with respect to x. Yeah, I know these graphs get ugly fast. Oh, and one last point I want to make. Again, this point is S of x is equal to d of x, right? And it is the point A P naught, or x naught, P naught, however you want to denote it. So, with this in mind, we are given an example where we have a demand function and a supply function. Remember here with demand functions and supply functions that X is going to be the number of units and P is going to be the cost. Or the price, rather. So what we're going to do, I'm going to jump to the next slide and show the graph here. What we're going to do is find the point of equilibrium. We're going to find the producer surplus and the consumer surplus. All right. Going back to that previous slide, our demand function is going to be negative 0.36x plus 9. Our supply function is going to be 0.14x plus 2. Now we're going to set these two things equal to each other. E of x equal to S of x. We do this so that we can get that point A and P naught, right? Which for the sake of brevity, I'm just going to refer to their solution, which is A P naught is equal to 14,396. 14,396. Okay. So, first thing we need to know is that we're going to be setting a function equal to just the constant P naught, right? So, when we find the producer surplus, AP, that's going to be integrated from 0 to 14, agreed? 0 to 14. The producer surplus is going to be our demand function compared to that line y is equal to 3.96, right? So 3.96 let me actually write it this way. P naught minus, my mistake, I meant to say supply function, not demand. So the producer surplus is going to be that line, y equal to P naught, minus our supply function. So this comes out to be the integral from 0 to 14 of 3.96 minus this function, which is going to be 0.14 x minus 2, all integrated with respect to x. That's our producer surplus. Now, the consumer surplus, this thing is going to be AC is equal to, again, we're integrating from 0 to 14. But this time, our demand function is what's the largest value, right? So it's going to be dx minus P naught integrated with respect to x, or can rewrite all this as 0 to 14 of negative 0.36x plus 9 minus 3.96 dx. Now we're going to do this integration. So just jumping ahead, how they have it set up, right, for the consumer surplus. So what we've got here, consumer surplus. They say that it's the integral from 0 to 14 of negative 0.36x plus 9 minus 3.96 integrated with respect to x. So it's exactly the same, right? That's what we've got down here. And now the producer surplus, it's the integral from 0 to 14 of 3.96 minus the quantity 0.14 times x plus 2 integrated with respect to x. It's exactly what we've got here. We just went ahead and distributed that negative sign through. Everybody cool with this? From here, again, we just do the calculus, apply the integration, then calculate those bounds, right? The difference at those bounds. And then we just do the arithmetic. A lot of this is just really going to come down to rinse and repeat. Having said that, do we have enough time? No, we don't. Okay. Having said that, there's one last problem that I want to go over. So in this problem, we are looking at slide 62. In this problem, we're given two different functions. These functions are modeling the projected consumption of petroleum. And what we're trying to find is what the difference in total consumption is going to be. So the first equation is the projection. Projection tells us that we're thinking it's going to be something like 0.004 t squared plus 0.330 t plus 383. And in the second, in the actual model, so what actually happened, what this problem is saying is they think C1 is going to happen. What actually happens is C2. That's going to be the equation 0.005 t squared, excuse me, 0.301 t plus 38.2. Okay, to set up this problem, we're going to want to look at the two functions and compare them. They're really close. They're almost exactly equal. So it's going to be hard to do this graphically without zooming in on a lot of different parts of this function. The point, though, is that C1 is greater than C2 on our entire boundary, which I forgot to write up here. Now, we want to find the total difference. So the total amount saved by what actually happened compared to what was projected. Make sense? What this is going to end up looking like, it's going to be an integral. It's going to be the integral from 0 to 30 of C1 minus C2 integrated with respect to t. Having set up this integration, once we throw in what our functions actually are for C1 and C2, we can simplify the integrand. Then we can do the integration. Then we can take the difference at the boundaries. Then we can do the arithmetic. And having said that, I will let y'all go. If y'all have any questions, feel free to ask. I'll stick around for a little while.